In this video, we will be learning about trigonometric identities and simplifying expressions using trig identities. We're going to start with the reciprocal identities and the quotient identities to simplify these expressions. In this first example, I'm going to rewrite cotangent as cosine x over sine x from above. So I get sine, well, in this case theta, times cosine theta over sine theta. And the sine thetas cancel out, leaving us with cosine theta. In the next one, tangent squared theta. Well, tangent is sine over cosine, so that's sine theta over cosine theta squared. Both are squared. And cosecant is 1 over sine theta squared. And I can think of those as each part being squared. So this is sine, when we square a trig function, we write the exponent after the sin or the cos. So this sine squared theta means sine of theta squared. The reason we don't put the 2 at the end is because then it will look like the theta is squared, but the whole expression is squared. Okay, and then we do over cosine squared theta times 1 over sine squared theta. 1 squared is just 1. And the sine squared thetas cancel out, leaving us with 1 over cosine squared theta. And 1 over cosine is secant, so we can simplify this by writing secant squared theta. Okay, next one we have cotangent theta, which we rewrite as cosine theta over sine theta. And it is divided by cosecant theta, which is 1 over sine theta. And remember, when you divide by a fraction, you multiply by the reciprocal. So this is cosine theta over sine theta times sine theta over 1. And again, the sine thetas cancel out, leaving us with just cosine theta. So we simplify as much as we can until we have a nice simple expression. And in part D, secant squared theta is 1 over cosine squared theta. Cosecant squared theta is 1 over sine squared theta. And again, we take our first fraction, the top fraction, leave it alone, flip the bottom one, and multiply by the reciprocal. And nothing's canceling out, but I end up with, if I multiply top times top, sine squared theta over cosine squared theta. And sine over cosine is tangent, so I could rewrite this as sine theta over cosine theta squared, or tangent squared theta. In this next part, we're going to look at even and odd properties and Pythagorean identities. Cosine and secant are our only even functions. If you think about a cosine graph, it looks sort of like this. And it's symmetric about the y-axis. And if you remember even functions, a property of even functions is f of negative x is equal to f of x. So cosine of negative theta is cosine theta. Same with secant. It's also an even function. It's symmetric about the y-axis. So secant of negative theta is equal to secant of theta. The other 4 trig functions are all odd functions. So if you picture, for example, sine theta looks like this. And if you remember, sine theta, or an odd function is a function who is symmetric about the origin. If you rotated it 180 degrees, it would look the same. If you turn it upside down, it looks the same. So a property of odd functions is f of negative x is equal to negative f of x. So for all of our other four functions, sine, cosecant, tangent, and cotangent, if you take, for example, sine of negative theta, you get negative sine theta. That negative sign essentially moves outside. Okay, so using these properties, first I'm just going to use the even-odd properties. For cosecant, that's one of our odd functions, so the negative comes out front. And for cosine, it's an even function. Cosine of negative theta is just cosine of theta, so the negative goes away. And then I simplify. Negative cosecant is negative 1 over sine theta times cosine theta. And if I do top times top, bottom times bottom, I get negative cosine theta over sine theta, which is negative cotangent theta. In the next one, again, I'm first going to apply my even and odd properties. Secant of negative theta, it's an even function, so we get 1 over secant theta. That negative goes away. Tangent is odd, so the negative comes out front. And I don't do anything with my cosecant theta. I'm going to move that negative way out to the front. And 1 over secant is the same as cosine theta. Tangent theta is sine theta over cosine theta. And cosecant theta is 1 over sine theta. And my sine thetas are going to cancel, and so are my cosine thetas. And we just end up with negative 1. Now we're going to look at our 3 Pythagorean identities. These come from the Pythagorean theorem. Sine squared theta plus cosine squared theta equals 1. Tangent squared theta plus 1 equals secant squared theta. And 1 plus cotangent squared theta equals cosecant squared theta. So we're going to simplify some trigonometric expressions using these properties. In the first one, we can see that we have secant squared theta minus 1. One of our properties up here is similar to that. I see a secant squared theta, I see a 1. If I take tangent squared theta plus 1 equals secant squared theta and manipulate it a little bit, I'm going to move that 1 over to the other side by subtracting it. I get tangent squared theta equals secant squared theta minus 1. And that's exactly what I have up here. So I can replace secant squared theta minus 1 with tangent squared theta. And then on the bottom, for now, I'm going to leave sine squared theta. And then I'm going to simplify. So tangent squared theta is sine squared theta over cosine squared theta over sine squared theta. Now, since I'm dividing by sine squared theta, which is like sine squared theta over 1, that's the same as sine squared theta over cosine squared theta times the reciprocal, which is 1 over sine squared theta. And my sine squared thetas cancel, leaving me with 1 over cosine squared theta. And that would be the same as secant squared theta. In this next one, we have 2 terms, so I think I'm going to try and combine them. And first I'm going to write them both as fractions. So tangent is the same as sine theta over cosine theta. Minus, I'm going to rewrite secant theta as 1 over cosine theta over sine theta. And that's the same as sine theta over cosine theta minus 1 over cosine theta sine theta. To get common denominators, I'm going to multiply this left-hand term by sine theta over sine theta, which is just equal to 1, but that will give me sine theta cosine theta in the bottom. So this first term will become sine squared theta when I multiply the tops over sine theta cosine theta minus 1 over cosine theta sine theta is the same as sine theta cosine theta. So I have common denominators. The bottoms are the same. I can combine these into one fraction. the top will become sine squared theta minus 1 over the bottom, which is sine theta cosine theta. And now I'm going to use a Pythagorean identity. Up above, we have sine squared theta plus cosine squared theta equals 1. Sine squared theta plus cosine squared theta equals 1. If I manipulate this a little bit and I subtract the 1 over to the left side and the cosine squared theta over to the right side, I'll get sine squared theta minus 1 equals negative cosine squared theta. And so now I can replace this expression with negative cosine squared theta. So we get negative cosine squared theta on the top. On the bottom, we have sine theta, cosine theta. And one of the cosine thetas on the top cancels with the cosine theta on the bottom. So we end up with negative cosine theta over sine theta, which is equal to negative tangent theta. And here's one more example. First I'm going to distribute, and I'll get cosecant squared theta minus cosecant theta sine theta. Cosecant squared theta minus, well, cosecant theta times sine theta, those are reciprocals. If cosecant theta is 1 over sine theta, and if I multiply that by sine theta, I'm just going to get 1. So this is cosecant squared theta minus 1. And I believe that's one of our identities from above. So if we look above, we have this one right here, 1 plus cotangent squared theta equals cosecant squared theta. And if I manipulate it a little bit, I'm going to move that the 1 to the other side. I get cotangent squared theta equals cosecant squared theta minus 1. And that's what I have right here. So I can replace that with cotangent squared theta for my final answer. Here are a few examples where we are establishing identities, meaning we're manipulating one side to show that it's equivalent to the other. Or we might manipulate both sides to show that the two are equivalent. As long as you end up showing that the two sides of the equation are equivalent, that's fine, but you have to show all the steps. So I'm going to manipulate the more complicated side in part A. I'm going to take the tangent theta over secant theta and use my quotients. Tangent is the same as sine over cosine, so this is sine theta over cosine theta over secant is 1 over cosine theta, and I want to show that it's sine theta, so I'm going to keep going until I show that. I can rewrite this as sine theta over cosine theta times the reciprocal. When we divide by a fraction, we multiply by the reciprocal, and those cosine thetas cancel out. So when I cancel those, the left-hand side becomes sine theta, which is now equal to the right-hand side, and we've proved that those two expressions are equivalent. In the next one, I'm going to start, again, I'm going to work on the more complicated side until I get the left side, until it looks like the right side. I think I can use a Pythagorean identity for this inside part. So from our Pythagorean identity list, we have the property tangent squared theta plus 1 equals secant squared theta. And I can manipulate it. This is the same as tangent squared theta equals secant squared theta minus 1. I subtracted the 1 over to the other side. And so I can replace secant squared theta with minus 1 with tangent squared theta. So we get cotangent theta times tangent squared theta equals tangent theta. Now, cotangent is cosine theta over sine theta. Tangent squared theta is sine squared theta over cosine squared theta. And the sine theta on the bottom left will cancel with one of the sine thetas from sine squared theta. The cosine theta cancels one of the cosine squared, one of the cosine thetas on the bottom. So we end up with sine squared, or just sine theta left on the top and just cosine theta left on the bottom. And that is tangent theta. So now we've showed that the left-hand side does equal the right-hand side. And one more example like this where we establish the identity. This one looks like it's going to be a little more work. Usually when you have addition or subtraction, you're going to need common denominators to combine your terms. So to add 1 plus tangent theta, I'm going to write these as fractions and use common denominators. So first of all, this is 1 plus sine theta over cosine theta over 1 plus cosine theta over sine theta. I'm trying to make it equal tangent theta. Now the one on the top, I'm going to multiply by cosine theta over cosine theta so that I can add it together with the other term on the top. And on the bottom, I'm going to multiply by sine theta over sine theta to get common denominators on the bottom. So on the top, I can add those together, and I'm going to get cosine theta plus sine theta over cosine theta. On the bottom, if I add the tops together, I'm going to get sine theta plus cosine theta over sine theta. And then when we divide by a fraction, we multiply by the reciprocal. So I'm going to leave the top fraction the same and multiply by sine theta over sine theta plus cosine theta. And the top left and bottom right are equivalent expressions, so they cancel out. And we end up with sine theta over cosine theta. And sine theta over cosine theta is tangent theta. For our last two examples, we're going to use some other identities called the double angle identities. These are not all of the trig identities out there. There's even more than this, but we don't want to get too overwhelmed. But here's a few more. So again, we're going to be establishing the identity. And again, I'm going to start on the more complicated side and see if I can make it equal the other side. Using the identities in this box. So starting with this left-hand side, I'm going to probably go the common denominator route again. So cotangent theta is cosine theta over sine theta. Tangent theta is sine theta over cosine theta. On the bottom, we get cosine theta over sine theta plus sine theta over cosine theta. And we're hoping to show that this equals cosine of 2 theta eventually. Now, to get common denominators on the top, my left-hand fraction needs to get multiplied by cosine theta over cosine theta, and the right one by sine theta over sine theta. That way the denominators will both have cosine theta and sine theta as factors. And then on the bottom, I'm going to multiply by cosine theta over cosine theta for the left-hand fraction and sine theta over sine theta on the right-hand fraction. And so we get cosine squared theta minus sine squared theta, if we combine them into one fraction, over cosine theta sine theta. On the bottom, we're going to get cosine squared theta plus sine squared theta over cosine theta sine theta. And we're still hoping to end up with cosine 2 theta somehow. Since I'm dividing by a fraction, I'm going to multiply by the reciprocal, but I'm also going to use some of my identities at this point because if I look up at the box above, I see cosine squared theta minus sine squared theta, and that's what I have right here. So I can replace that with cosine 2 theta. And I'm not going to do anything with cosine theta, sine theta. I'm going to multiply by the reciprocal of the bottom fraction, but I do have a Pythagorean identity right here. Sine squared theta plus cosine squared theta equals 1 is one of my Pythagorean identities. So this expression right here is equal to 1. So if I multiply by the reciprocal, the 1 will go to the bottom, and we'll have cosine theta, sine theta on top. And now I can cancel the cosine theta, sine theta on the bottom left and top right, and I do end up with just cosine 2 theta on the left, and we have showed that the left-hand side does equal the right. And one last example. In this next one, I'm going to start off with cosecant 2 theta. I'm going to rewrite that as 1 over sine of 2 theta. And on the right-hand side, I'm going to write this as 1 over 2 cosine theta sine theta. And if we look up at our identities, we have this identity right here, sine 2 theta equals 2 sine theta cosine theta. So I can kind of replace either side. If I get leave 1 over sine 2 theta on the left-hand side, I can rewrite the right-hand side, replace 2 cosine theta sine theta with sine 2 theta. And I have showed that those two are equivalent expressions.